This afternoon we'll be focusing on the solutions and the global policy implications of the disaster. Our first set of speakers for the afternoon session are Daria Hirniak and Karim Khan. Daria Khan is senior engineer at Bechtel, and Karim Khan is a project control manager at Bechtel. And both of them worked in Slavutic, Ukraine, working on the shelter implementation plan. So many of you have heard about the plans to remedy and cover the sarcophagus, and today you'll hear from two professionals who were directly involved in the shelter implementation plan. They'll be presenting together.
Good afternoon, everyone. Karim and I were living and working in Slavutic, Ukraine from the years of 2000 through the end of 2004. At the time, I was a project manager for Bechtel, managing the preparatory works projects, which we'll talk about in a moment. And Karim was working with Bechtel, and he was the project controls manager for the project, managing the funds, the costs, estimating, and the schedule. Today, we both work for Bechtel. We live in Washington State and working on the $10 billion project that is a waste treatment facility at Hanford. Today, we're going to describe ongoing remediation at the Chernobyl nuclear power plant, specifically the shelter implementation plan. The goal of the To set the stage, we'll briefly describe the construction and current condition of the existing shelter object and present a short video. Then we will describe the shelter implementation plan, how it is organized, funded, and how it's managed. We will then describe in more detail the specific scopes of work that are planned and are ongoing. As you know, the shelter was constructed in horrific conditions. There were doses of up to 2,000 rem per hour. Many of the workers had died of radiation exposure or were permanently disabled in some way. But within 7 months of the accident, the destroyed reactor was encased in a massive structure to confine the damaged nuclear fuel and destroyed equipment, and to reduce the likelihood of further releases of radioactivity into the environment. This entombing probably gave it the name the sarcophagus. Formally, the name of the structure that's been built is Objekt Ukrytya, or in English, the shelter. To construct the shelter, there was about 400,000 cubic meters of concrete and 7,000 tons of steel. To understand, I'd like for you to see what we started off with. We have the existing unit, remains of existing Unit 4. It's too difficult to see. Oh, we will go to the next one, apologize. On the north side of the reactor, the walls had been destroyed completely. So there was a cascade wall that was built in 3 levels, and then atop of it, a shorter buttress wall was placed on top. The next portion, the roof covering, was placed. What we have is, it was placed, the beams that support the roof were supported by remains of the existing shelter. On the west side were the remains of the existing Unit 4 walls. On the east side, they used the remains of the ventilation stacks. The steel beams were placed, and then on top of those steel beams were placed pipes to provide the covering. Overall, there were 27 pipes, approximately 1.2 meters in diameter and about 35 feet in length. Another component of the shelter was the western buttress wall, steel walls that we see on the right. They were fabricated elsewhere, away from the contaminated area, then brought to site, and then by crane placed adjacent to the western wall. The intent initially was for those walls to be welded together and concreted, but the levels were just too high. Another problem there was in placing these walls, there was no opportunity to provide structural backfill. So whatever fill there was, and that the walls were placed. Now, to have an appreciation of the conditions in which the workers worked and the massiveness of this entire structure, we'd like to show you a brief video of its construction.
смотри куда. Ниже, вот самое разрушенное место, вот сюда вот. Во-во-во-во-во-во.
Housing personnel from the Chernobyl nuclear power plant. It is now deserted, save for a few research workers. It is located 2 miles from the 4th unit at Chornobyl, site of the explosion in April 1986. You will see a brief video chronicle of the sarcophagus construction.
Mere end 100.000 mennesker evakueret fra 30 km-zonen rundt om Tjernobyl atomkraftværk.
On Monday, April 28th, the alarm was raised at the Forsmark nuclear power plant in Sweden. For the first few days, the Soviet Union released no information about the accident. The explosion had expelled a huge cloud of radioactive dust. For 24 hours, it drifted across the territories of Ukraine, Belarus, Poland, and then dispersed over the northern hemisphere. Here we can see the breach between the 3rd and the 4th units. This is what the north side of the 4th unit looked like. The level of radiation at this point reached 2,000 Roentgen per hour. The roofing of the 4th unit turbine hall was destroyed by the fire and falling debris. At the time of the accident, fragments of reactor fuel core, highly radioactive fragments of nuclear fuel and graphite were expelled from the roof of the 3rd unit. April 30th, radiation was 340 Roentgen per hour at a height of 200 meters above the reactor. At this point, people had little idea of the gravity of the accident. Emergency workers had no experience of working in such conditions. The instruments they were using had to be designed especially for high radiation fields. Emissions of radioactive substances from the reactor continued. Radioactive dust continued to drift, polluting the air and the land. Helicopters attempted to decontaminate the area using a special agent. Every possible effort was made to prevent the fire from spreading from the 4th to the 3rd unit via the shared service lines. A considerable amount of nuclear fuel in the form of clinker, fine dust, and newly formed substances containing uranium had accumulated under the reactor at the time of the accident. By summer of 1986, the first radioactive dust cloud had destroyed 4 square kilometers of forest. The forest had absorbed several million curie of radioactivity. Hundreds of miners began constructing a tunnel under the reactor. At the same time, a Moscow research institute was testing tablets of nuclear fuel. There was a fear of a meltdown at the reactor base following the failure of its cooling system. Fortunately, this new catastrophe failed to materialize. Special diagnostic devices containing instruments to measure temperature and radiation were used to investigate the scene of the explosion. The first 4 devices of this kind were lowered into place by helicopter on the 4th of August. Some recalled that the perilousness of the work provided its own inspiration. The government attempted to encourage this effect by means of patriotic slogans. This one says, "The power of friendship between the peoples of the USSR is stronger than the atom." It was clear that the ruins of the unit could not be left as they were. They continued to deteriorate and remained a strong source of radiation. The most dangerous area would be surrounded by a 200-kilometer-long road. 3 plants producing concrete were built not far from the power plant. The first one was commissioned on June 21st. Then began construction of the shelter, the so-called sarcophagus. Due to the high level of radiation, it was impossible to remove all the construction debris from the site. Devices under remote control were used for carrying out most of the work. The metal frames were constructed at a distance, brought to the unit by rail, and then sunk in concrete. About 700,000 tons of soil had to be removed from around the power plant. Then reinforced concrete plates were laid. The north part of the sarcophagus was built as an inclined wall. Radioactive fragments and soil were buried in the foundation of the first tier. This work was completed by the end of July. The 12 meters high second and third tier shells were mounted and grouted in concrete in August. Since there was still heavy radiation, specially protected machinery was used for the work. Concrete was brought in through hundreds of meters of specially constructed pipes. On September 14th, the fourth tier casing of the cascade wall was erected. By that time, about 100,000 cubic meters of concrete had been used for the construction of the wall. The time had come to begin mounting the ceiling. Victims of the catastrophe were not only human. Vehicles, which were irretrievably contaminated, were transported to a cemetery in the Chernobyl zone. All these vehicles are still there. Among them are buses and helicopters, military and civil trucks, ambulances and fire engines. The ceiling is now assembled and ready for fitting. Installation of the ceiling continued for more than 48 hours. Reinforced concrete ventilation shafts still standing after the accident were used as foundations for the ceiling. After the accident was a full seismological investigation of the region held. It is now known that the area is prone to earthquakes measuring up to 7 degrees on the Richter scale. Soldiers from the Chemical Protection Corps carried out decontamination of the reactor room for the first and the second units. A few months later, these units will be operational again. Steel pipes about 35 meters long are being lifted to the ceiling. According to the project plans, there will be 27 such pipes installed. Soviet leaders had tried to convince 47,000 evacuated inhabitants of Pripyat that they could return to their homes. At the time this film was taken, government assurances had proven to be worthless. Like Hiroshima and Nagasaki, Pripyat joined the list of towns conquered by the atom. Flying near the plant, we can see the cockpit protected by lead and concrete, from which specialists supervise the progress of construction. The roofing will cover unexamined areas of the reactor, including its upper plate, which weighs almost 3,000 tons and stands vertically after the explosion. Diagnostic instruments attached to the plate are clearly visible. Construction of the south part of the roofing is finished. The west wall, which remained after the explosion, is shielded by a metal covering 50 meters high. Construction is finally over. The long, dangerous flights are also at an end. The shelter seems to be solid, but tons of nuclear fuel remain under an unsealed sarcophagus. Steadily corroding and resting on unstable foundations, the shelter becomes ever more dangerous. The Chernobyl problem is still unresolved.
Now, as you could see, the construction of the shelter was done in horrid conditions, and it didn't allow for construction to be done according to norms. There were, because of the situation the way it was, connections that would have to have been welded or would have been bolted could not take place, and we mostly rely on is on just friction connections. And the condition of the shelter has deteriorated over time and poses an ongoing potential risk. There's a constant structural deformation of that facility. At the time of the shelter's completion, the openings of the roof and walls amounted to a total of about 1,000 square meters. That was just at the time of construction. Leaks in the roof have allowed the penetration and accumulation of large amounts of rainwater that are now highly radioactive. This has also created a condition of high humidity within the shelter, producing corrosion of the metallic structures within, further destabilizing the structure. Under the influence of atmospheric precipitation and temperature changes, the condition of the highly contaminated, highly radioactive fuel-containing masses has deteriorated, turning it into a dust form. And this represents an essential menace in case of distribution of radioactive pollution. So what's the plan forward? It's the shelter implementation plan. And Karim will introduce that plan to you.
Okay, so this brings us to the internationally agreed approach to addressing the issue of the deteriorating sarcophagus in Unit 4. This approach, as we've said, is called the Shelter Implementation Plan. The approach was developed in a joint effort by an organization called Technical Assistance to the Confederation of Independent States, or TASIS, the government of Ukraine, and the U.S. Department of Energy. And as we said, it's the project that Daria and I worked on between 2000 and 2004. I'll first give a short summary of some key events that led to SIP, and then I'll present an overview of the plan, the recommended course of action, and its 5 main objectives. The first step towards international cooperation in addressing the risk of the deteriorating shelter was in 1992 with the international competition for the best project and technical solution for converting the shelter into an environmentally safe system. At that time, the competition jury adopted the concept of a step-by-step conversion. Further analysis and monitoring, informing the community, stabilizing the shelter, constructing a new enclosure, constructing radioactive waste facilities, and ultimately removal and storage of radioactive materials. In 1995, a feasibility report was issued by the Alliance Consortium that concluded that the shelter was unstable and that it was necessary to construct an enclosure to be able to eventually dismantle Unit 4. This report also concluded that Ukraine was not able to finance this project by itself and that the international community needed to assist. In 1996, the recommended course of action was developed. This defined the Shelter Implementation Plan. And it's important to note that the SIP is not an explicit technical solution, but rather a systematic approach to finding the optimized solution. And in 1997, the G7 adopted the SIP, and the donor countries held a conference in New York where they assumed an obligation to allocate money for the project, and the Chernobyl Shelter Fund was established. The recommended course of action is broken down into 3 phases. Phase 1, stabilization and other short-term measures, which is basically preparing the shelter and the site for the new safe confinement. Phase 2, preparation for conversion into an environmentally safe site, which is the design and construction of the new safe confinement. And Phase 3, conversion into an environmentally safe site, ultimately the deconstruction of Unit 4 and the storage of radioactive waste. The SIP covers the first 2 phases. The recommended course of action, phases 1 and 2, are further broken down into 5 main objectives. Reduction of accidental collapse potential, reduction of accidental collapse consequences, improvement of nuclear safety, improvement of worker and environmental safety, and development of a long-term strategy and study for conversion to an environmentally safe site. These 5 main objectives are further broken down into 22 tasks that encompass programmatic, regulatory, and task milestones. So as we said, the SIP is not an explicit technical solution, but rather a systematic approach to finding the optimized solution. This means that there are or were several key decisions that needed to be made when further data gathering and analysis made sufficient information available to the decision makers. These decision points are captured as the 10 programmatic milestones and cover which stabilization measures to implement, the required monitoring, what to do with the water that was inside the shelter, what to do with the fuel-containing material, and the type of the new confinement building. And what this slide shows here are 2 alternatives that were considered for the new confinement. One is the arch, which is what was decided on, and the one below it is called dock caisson, and that was another approach. The funding for the SIP is called the Chernobyl Shelter Fund, or CSF. The money is provided by the donor community made up of the G7 nations, the Ukrainian government, and I believe 14 other nations. The fund is administered by the European Bank of Reconstruction and Development, or EBRD. They make the fund available to the project in the form of grants for various specific scopes of work. And the recipient of the fund is the Chernobyl nuclear power plant. So the client and legal entity responsible for the SIP is CHMPP. And as the client, CHMPP has the right to review and approve the design, procurement, and construction work plans related to SIP. However, since the West is putting up most of the money, work activities are subject to review by the EBRD on behalf of the donors. A project management unit was created to provide project management services and oversee the execution of the SIP. Daria and I work for this PMU. It is comprised of Ukrainian client personnel from CHMPP, consultant personnel from the consortium of Bechtel, Électricité de France, and Batel, and local Ukrainian support staff. The project management services include program and technical management, procurement, and project controls. Now Daria will talk about some of the major scopes of work.
There are basically 5 major scopes of work. The first is the preparatory works. This is the design and construction of facilities and utilities to support the SIP. People have been there know that the site is basically derelict and the basic infrastructure needs to be upgraded before we can do the next massive steps of the stabilization efforts in safe confinement. The stabilization. This is the design and construction of a few specific measures to strengthen and stabilize the existing shelter. Stabilization measures are intended to have a design life of 15 years. Auxiliary systems. This is the design and construction of access control and monitoring systems, plus the procurements related to radiological and industrial health and safety. Fuel-containing material. This will be the study of fuel-containing material in order to decide what to do with them. And with next, the new safe confinement, this is by far the biggest piece. The design and construction of the arch will be constructed in front of the existing shelter, then slid over on top of it, sealing both ends. The projects that I was project manager over are the preparatory works. A big project was the change facility, which was for 1,430 persons, and it provides the care and control of workers in their daily process of work clothes changing, radiological monitoring, and access to the work in the radiological controlled areas of the site. The facility also includes emergency medical response facility and control of medical emergencies, as well as the capability of the routine medical screening of personnel. Small Strebaza is a construction operation base. It's critical to the effective construction management. There's an administration building that will house the offices of the PMU. There's warehousing and unloading capabilities with railroad access and a laydown area. The upgrade of utilities is a significant activity by itself. It's composed of 8 separate projects constructed to provide the essential power, water, sewerage, and communications to support the demands of the future construction and the new safe confinement operations. The training center will provide the practical and theoretical construction training to the construction workers for stabilization and safe confinement, and provide also the client contractor indoctrination. The training center has 2 facilities, one in the city of Slavutic, where the initial training will begin. Workers will actually be living there while they are prepared for their work in SIP. There's also another training facility which is located closer to the shelter in the industrial zone. And that is a key part of the training because it allows for a mock-up site where workers will practice before going into the shelter object. We're going to talk about stabilization efforts, and in some areas where stabilization is going to be carried out, a worker could only be there for no more than 15 minutes. So it's essential that the worker knows step by step what he needs to be performing once he's at the site. So this allows for having hands-on training on the mock-ups. We also have a rehabilitation center. There's 2 facilities. One is located in the change facility on site, and another rehabilitation center is located in the city of Slavutic. That's where the workers will first be screened for medical conditions and to get the appropriate approval for proceeding with work. Now we show an example here. This is the training center in Slavutic. When Slavutic was built, there was a lot of construction going on, but money ran out and not all construction was completed. So our effort in SIP was to utilize as many of the existing facilities as possible. On the left, what you see is the construction of what was to be a kindergarten, and that is what we converted to the training center with a 100-room hotel. As we said, the purpose of stabilization is the design and construction of specific measures to strengthen and stabilize the existing shelter. Originally, there were 29 stabilization measures contemplated, but doing a dose cost-benefit analysis, it's been decided to do 10 specific measures. Summarizing overall, the stabilization measures will be the support of the roof beams, the western buttress wall, the aerator corridor, the northern buttress wall, and southern roof panels. Karim will now speak to you on the auxiliary systems, the fuel-containing masses, and the construction of the new safe confinement.
We've talked a little bit about auxiliary systems already. This is the design and construction of access control and the monitoring system, plus the procurements related to radiological health and safety. Access control is the system of perimeter fencing, security, turnstiles to control the flow of personnel working on the site. Monitoring includes seismic monitoring for earthquake activity, neutron monitoring. When the accident occurred, much of the nuclear fuel melted, mixed with other materials in the core, and ran through the piping into many parts of the building. It has different forms, including a lava-like form and a pumice-like form. Its behavior remains the focus of investigation and monitoring. The pictures that you see here are a couple of examples of the lava-like form. And I'm sorry, it's kind of cut off a little bit on the bottom, but the person in the extraordinary photo on the right is taking measurements next to a lava-like form called the elephant's foot, where no doubt the radiation levels are probably lethal within a matter of minutes. Most of the work related to FCM has been postponed because it's anticipated that when it comes time to actually remove the FCM in some 50 years, the technologies related to the prototypes and removal strategies that are developed now will be obsolete. In 50 years, it's hoped that there will be the deep geologic repositories constructed to place the material when it's removed. The largest single task of the SIP is the implementation of the new safe confinement. The purpose of the new safe confinement is to stop the intrusion of rainwater, prevent airborne transport of dust, and to enable deconstruction. This effort currently involves 3 major scopes of work: site clearance and grading, final design and construction of the arch and foundations, which includes deconstruction of Ventstack 2, which currently serves units 3 and 4. The scope of the construction of the arch includes foundations and slideways, the structure itself, including roof and end walls, the preparation and use of the assembly and erection area, and the supply and installation of the required equipment in the arch structure. The principal dimensions of the arch are a span of 250 meters, a length of 150 meters, a height of 100 meters. Its weight is 22,000 tons. There'll be 4 50-ton cranes, and it has a design life of 100 years. We'll conclude our presentation with a short video showing how stabilization and new safe confinement will be constructed. Thank you.
Stabilization is the first and foremost primary effect the SIP has on improving the safety. One emergency measure has been completed, the stabilization of the western support beams B1 and B2. Presently, as an integrated set of measures, the follow-on stabilization activities are governed by the principal conceptual design decisions of SIP labeled as P1 and P2. These decisions and the subsequently designed measures represent the primary structural modifications of the shelter, considering an operational life of nominally 15 years. 5 measures are agreed upon for implementation, namely Measure 2, 3, 5 and 11, and Measure 8. Measure 2 is the west wall stabilization, western zone. The accident explosion caused a section of the shelter's western wall to lean westward. An extreme seismic load east to west could result in opening the external covering of the shelter with the consequent potential release of radioactivity and movement of debris and FCM. Stabilization is planned for the long term by erecting a structure of 2 49-meter high towers on substantial foundations outside the buttress walls. The towers are to be linked up with space frames at 3 levels. Level 1, a girder tied to the ends of beams B1 and B2 to resist the inertial force of the wall and beams B1 and B2. Levels 2 and 3, girders connecting the towers with horizontal supports to resist the inertial forces of the existing reinforced concrete framing and western buttress wall. Measure 3 is the deaerator corridor stabilization, southern zone. The accident explosion forced the deaerator frame columns to lean toward the turbine hall. The V-shaped props previously installed are unable to withstand potential north-south seismic loads. Stabilization is planned by strengthening the V-shaped members with additional lateral struts and connecting the bearing parts of cross pieces and columns. Measures 5 and 11 are listed together as they work integrally as measures on the northern zone. The northern buttress wall is not strong enough to bear the weight of the northern hockey sticks due to sections of missing concrete dating from the original shelter construction. Lack of rigid cross ties between the hockey sticks and the northern buttress wall could cause the sticks to shift under extreme wind loads. Stabilization is planned by establishing holding anchors and placing concrete in the upper part of the northern buttress wall casing as an integrated measure. Measure 8 is the southern zone roof stabilization of the southern hockey sticks and roof panels. 4 additional measures are contemplated and have been designed, but are further subject to dose cost-benefit analysis prior to their implementation, mainly measures 4, 14, 14A, and N/N. Stabilization construction activities are scheduled to start at the end of 2003, with work execution plan preparation and site mobilization. Internal stabilization measures construction is scheduled to start in the second quarter of 2004 and be completed by the end of 2005. This portion of the presentation covers the new safe confinement conceptual design. This movie was prepared using a 3D CAD model. It presents the current design status prepared by the team of engineers from Bechtel, EDF, Battelle, and the Ukrainian subcontractor, KSK. At this time, the conceptual design is complete and the tender and licensing documents are under preparation. The main purpose of the NSC arch is to confine the radioactive materials and limit the rainwater incursion, as well as to initiate the deconstruction activities for Unit 4 of the Chernobyl nuclear power plant. The construction work on site begins with the arch foundation. The foundation work begins in the erection and sliding areas, thus allowing the erection work to begin as soon as the sliding paths are completed. Then the work extends toward Unit 4. The foundation consists of a 3 to 4 meter thick by 18 meter wide concrete pile cap supported by deep concrete walls, shown here in the cross-section. The contaminated topsoil layer will be removed prior to construction of the foundations, thus minimizing schedule risk and radiation exposure to workers. As soon as the assembly area is ready, the arch construction work begins. The arch structural elements are pre-assembled in a shop and brought to the assembly area. The elements are as big as possible to minimize the assembly work on site. Some may be 65 meters long and may weigh up to 200 tons. The design team considered the use of a large crane to erect the pre-assembled elements. This was presented in our previous movie of the conceptual design in March of 2003. An alternative method has now been considered, using strand jacks for the erection of the arch. In this method, the arch elements are assembled into large sections on the ground. Each section consists of 3 arch bays. The end sections are pivoted on the foundation support and lifted by the strand jack towers. The middle section is then assembled, lifted by the strand jacks, and connected to the end sections. The strand jack towers are then moved inward to clear the arch. After completion of the first 3 bays by this method and erection of the east wall, the first quarter of the arch is moved eastward. This short sliding clears the erection area, now permitting the erection of the subsequent 3 base sections of the arch. The erection activities shall be conducted as much as possible in the assembly area. That will include the installation of the bridge cranes, end walls, and cladding in the arch structure before the sliding. Once the entire arch is assembled, it is moved over the object shelter. The structure is supported by steel distributing beams sliding on Teflon bearings. The pulling jacks are located at both far east ends of the sliding paths. A high-precision hydraulic integrated system controls the sliding forces applied on both sliding paths, allowing for a smooth movement. The final sliding is expected to last less than a day. It should also be noted that both the east and west walls are shaped so that they can be moved over Unit 4 with minimal additional work in the final resting place. After full commissioning of the arch, the deconstruction work can begin. The first structures that can be dismantled are the roof's shelter components, the southern panels, southern hockey sticks, the northern hockey sticks, and the eastern hockey sticks. Finally, the dismantling of the main beams takes place. The northern B1 beam, then the southern B1 beam. The deconstruction of the southern B1 beams shows the flexibility of the cranes. Beam B1 South is first lifted from its east-west position and then turned in the north-south direction using the capabilities of the trolleys to move from one bridge to another. Finally, the southern B1 beam is placed in the laydown area in the north-south direction. This flexibility of the cranes allows the rotation of the dismantled elements, thus reducing the arch length by 5 meters. Next, the mammoth beam can be deconstructed. The dismantling of this heaviest beam requires cutting it into 2 sections, which in turn will require an additional support. This video shows a temporary support tower. If this approach is not feasible due to instability of the deaerator stack, an additional bridge trolley can be used to provide the middle support. Next, the central hull is removed. Each dismantled structure will, from this point, be processed in the auxiliary storage buildings and eventually stored in the temporary storage designed under the arch. We hope that this video provides you with a clear idea of the work and progress being accomplished currently under the Chernobyl SIP project.
We hope that this gave you a good representation of what the Shelter Implementation Plan project is about. Karim and I are very appreciative of the opportunity to participate in this conference, and thank you for your attention.